I'm Ethan Davis.
I'm Ethan Haverty.
Alright, so for our experiment, what we were going to try to replicate and test here was take two blocks of different masses and shoot them into a wood block with different surfaces underneath to see how far that would travel. Meaning that the blocks are different masses, they're going to be traveling different velocities, because we wanted to see what kind of relationship that had between the velocities into the again different masses going into the same block. So what we had set up was we had just the wood block on a piece of acrylic sliding across um, the block on a piece of wood, just like a thin sheet of smoother backed wood, and then a piece of acrylic underneath the wood mated together, and then that would slide across the sheet of styrofoam, and then the block of wood by itself across the piece of styrofoam. And what we ended up coming up with as a whole was that the heavier plug moving at a slower velocity would push the block farther than what the higher velocity and the smaller weight plug would do.
The mass of the first plug was 0.00136 pounds mass, and the mass of the smaller plug, which I've labeled plug 2, is 0.000753 pounds mass. For the calculation, we have the mass is equal to, like I said, 0.001369 pounds mass. So the distance to get our velocity, we took the tube, it was 37.25, and we took the distance that the block moved. So for this example, it's going to be 47.167 inches. And then the average time, we had the timer that we used for the ping pong ball gun, and our average time was 0.010672 seconds. What's the symbol for average? Doesn't matter. 672 6 seconds. So the velocity of impact at equal to So there's the velocity of block number 1, or sorry, plug number 1, and that is the bigger plug. Now, I wanted to get the velocity of the second block to see, okay, once it's hit, how fast is that block moving? So I used the relation of mass of A, velocity A, plus mass of B, velocity B, is equal to MAVA prime plus MBBB prime. And since when the plug hits that block, all of its energy is transferred. This goes to 0. And since that second block isn't moving at the beginning, that also goes to 0. So you end up with MAVA is equal to MBBB prime. B prime is equal to MAVA over MB. So I'm going to come up here, running out of room, and that is 0.01369 pounds mass times 368.32 feet per second. wow, all over 0.062111 pound mass. Pounds mass cancel and you're left with feet per second. So your velocity prime B is equal to 8.12 feet per second. So after that, I wanted to find the time that it took this reaction to happen. Obviously, you're going 8.12 feet per second, but you're not doing that for a whole second because we got nowhere near 8 feet of movement from that other block. So to find the time of this reaction, I use the relation between force is equal to mass times acceleration. Acceleration is equal to velocity times time. So the force is equal to the mass times velocity times time. So time is equal to force divided by mass times velocity. So once you have that, time is equal to 0.359. This 0.359, before we did any testing with the plugs, we took up different blocks with the different surfaces, and we had a spring gauge, and we pulled them across the surface and found the force that it took to break that, kinematic friction? No.
Just static.
Static friction, there we go, static friction. And we use that as the force because that is technically the force that you require to move the block, to initially move the block. So our force is 0.359 pounds force, and then divided by the 0.062111 pounds mass times 8.12 feet per second. Apologize for the lack of room on this board. So there's that, and then on top of that, you have to multiply this by 32.2, and the time is equal to 0.02211 seconds. So it takes that long to move the distance, or to move the distances that we got at that speed. So I'm going to erase some of this. Velocity B. So B is equal to 8.12 feet per second. We could erase that. And then we need the time is equal to 0.02211 seconds. Pound of mass is 0.062111 pounds mass. Okay, yeah, we're good. So I'm going to erase all of this. Okay, so to find the force on the big block to get it to move that far, I use the relation mv1 plus force times time is equal to mv2. mv2. I apologize, this is the integral of time. So, and we're looking for force, so your equation is going to be force is equal to mv2 minus mv1 all divided by time. Now, your velocity 1, since the block is not initially moving, that is going to become 0. So your force is equal to, I'm going to do this over here. Your force is equal to 0.0621111 pound mass times 8.12 feet per second minus on my paper I worked out MV1 to B0, but in this we'll just put it as minus 0. All of that over 0.02211 seconds times the 32.2 for your pounds mass to get the pounds force. And then after that, we get force is equal to 0.712 pounds force. That seems reasonable. The block itself was actually 2 pounds, so to get a 2-pound block to move 10 inches or so, that seems reasonable. And then force, I just want to find the acceleration of it. So I did force is equal to ma, and then the acceleration was equal to 0.36 feet per second squared. Now some of these numbers, after I did the math, I was like, I couldn't figure out whether or not they were correct or not, using intuition, because it happens so fast, you can't really tell, okay, the velocity of the block was 8.12 feet per second. Well, how do I know that's right? It didn't even go a foot. So, all these numbers seem reasonable. I did the math for plug 2, which was the smaller plug. I did it the same way. I got a velocity here. I'm going to erase this. I got a velocity of plug 2, VP2, as 653.60 feet per second. I got the velocity of B, the block that we were shooting into, as 7.92 feet per second. I got the time to be 0.02265, which I found kind of odd because that's a little bit more than the heavier block. I thought this time would be a lot lower than that time, considering either A, didn't go as far, and B, it was going a lot faster. So then I have that time, and so the force, average force on the block, I got to be 0.674 pounds force, and the acceleration is equal to 0.337 feet per second squared. And like he said, we did these numbers for the acrylic on wood, the wood on wood, the acrylic on foam, and the wood on foam. I didn't do all the math for that on paper. I used an Excel sheet. I will submit the Excel sheet with this video. All the results they looked correct based on my intuition. The speed of all plug 2s were faster than plug 1, which they should be. All the forces of the plug 2 versus plug 1 were less, which I thought they should be because it has less mass. And then times were very similar, which I found a little odd. Not sure why, not sure how. But based on the numbers, I believe the experiment was done correct. We did only use, I believe, 5 psi.
Mm-hmm.
Yeah, 10 psi put a whole lot in the binder, so we decided to turn it down just a little bit. But that was our experiment. Here's our math.
Good. Good. Yep. Yeah. Right.
No, he tells them they're gonna catch it.
Yeah, I say I swallow.
Then you go through it.
Fire in the hole.
3, 2, 1.
I did.